In 2024, the United States placed advanced AI chips such as those produced by NVIDIA under strict export control. At first glance, this may look like a conventional trade policy move, another chapter in ongoing technology disputes. However, that interpretation is fundamentally incorrect. What we are observing is not a trade adjustment, but a structural shift in how states classify and control critical resources. When the movement of a single chip across borders requires government approval, the nature of that chip has already changed. It is no longer a commercial product operating under market logic. It has become a strategic asset governed by national interest. This shift marks the beginning of a new economic paradigm. In previous decades, globalization assumed that technology would diffuse across borders relatively freely, driven by efficiency and cost optimization. Today, that assumption is breaking down. AI chips are no longer evaluated solely by price-performance ratios or supply chain efficiency. Instead, they are evaluated based on geopolitical alignment, security implications, and long-term strategic positioning. In other words, compute is being reclassified from a factor of production into an instrument of power. This reclassification has profound implications. It means that access to compute is no longer guaranteed by capital alone. Even if a company has sufficient financial resources, it may still be restricted from acquiring the most advanced hardware if it operates within a jurisdiction that is not aligned with the exporting country's strategic interests. This introduces a new layer of risk that did not exist before: geopolitical access risk. Companies must now consider not only whether they can afford compute, but whether they are politically allowed to access it. From a systems perspective, this is the moment where AI infrastructure transitions from a decentralized global market into a controlled network of strategic nodes. Each node, whether it is a chip manufacturer, a data center, or a cloud provider, is increasingly embedded within a national framework. The idea of borderless AI is becoming less realistic. Instead, we are moving toward a world of fragmented AI ecosystems, each defined by its own regulatory environment, supply constraints, and strategic priorities. For operators and decision-makers, this creates a fundamental question. Are you building on neutral infrastructure, or are you building on someone else's sovereign system? Because once compute becomes political, every layer above it, data, models, applications, also inherits that political context. This is not a future scenario. It is already happening. And understanding this shift is the starting point for any serious discussion about AI strategy in the next decade. To understand why compute sovereignty is emerging as a defining issue, we need to place it within a broader historical pattern. Technological breakthroughs have always been closely tied to shifts in global power structures. In 1945, nuclear weapons redefined military dominance. In 1957, the launch of Sputnik initiated the space race, signaling that technological capability could translate directly into geopolitical influence. In the 1990s, the expansion of internet infrastructure created a new layer of economic and informational power, largely dominated by the United States. Each of these moments shares a common structure. A breakthrough technology emerges, initially framed as a scientific or industrial advancement. Over time, states recognize its strategic implications and begin to assert control. What follows is a period of competition, where nations invest heavily to secure dominance, or at least avoid dependency. Eventually, a new equilibrium forms, where the distribution of that technology defines the global hierarchy. Compute sovereignty is the next iteration of this pattern. Artificial intelligence is not just another software layer. It is a general-purpose technology that amplifies capabilities across industries. However, unlike previous digital tools, advanced AI requires enormous computational resources. Training state-of-the-art models is not something that can be done casually or cheaply. It requires specialized hardware, massive energy consumption, and highly optimized infrastructure. This creates a natural bottleneck. Unlike software, which can be copied and distributed at near zero cost, compute capacity is inherently scarce. It depends on physical assets, semiconductor fabrication plants, data centers, power grids, that cannot be scaled instantly. As a result, control over these assets becomes a source of power. Countries that can produce or secure large amounts of compute gain a structural advantage, while those that cannot are forced into dependency. What makes this moment particularly significant is the convergence of multiple layers of technology. Semiconductors, cloud computing, energy systems, and AI algorithms are all becoming interdependent. This creates a tightly coupled system where control at one layer reinforces control at others. For example, a country that dominates advanced chip manufacturing can influence who has access to high-performance computing, which in turn affects who can develop competitive AI models. In this context, compute sovereignty is not an isolated issue. It is part of a broader reconfiguration of the global technological order. Just as nuclear capability defined power in the mid-20th century and internet infrastructure defined power in the late 20th century, Compute capacity is poised to define power in the 21st century. The key difference is that this time, the competition is not only between states, but also between corporations that operate at a quasi-sovereign scale. Understanding this historical continuity allows us to see current developments not as anomalies, but as predictable outcomes of a recurring pattern. The question is not whether compute will become a source of geopolitical competition. It already has. The real question is how each country positions itself within this new structure, and whether it can secure a role that aligns with its long-term strategic interests. At the core of the compute sovereignty debate is not technology itself, but incentives. To understand how the system evolves, we need to analyze the motivations of the key actors involved. Broadly speaking, the global landscape can be simplified into three categories: the United States, China, and the rest of the world. Each operates under a distinct set of incentives, and the interaction between these incentives creates the structural tension that defines the current geopolitical environment. The United States' primary objective is to maintain technological leadership. This is not only about economic advantage, but also about national security. Advanced AI capabilities have direct implications for defense, intelligence, and strategic decision-making. By controlling the export of high-end chips and related technologies, the U.S. aims to slow down the progress of potential competitors while preserving its own lead. Export controls, investment restrictions, and domestic subsidies are all tools used to achieve this objective. China, on the other hand, operates under a fundamentally different incentive. Its priority is to reduce dependency and achieve technological self-sufficiency. From China's perspective, reliance on foreign technology, especially from a strategic competitor, represents a systemic vulnerability. As a result, China has been investing heavily in domestic semiconductor development, alternative architectures, and vertically integrated AI ecosystems. The goal is not necessarily to surpass the U.S. immediately, but to ensure that critical capabilities cannot be cut off. The third group consists of all other countries, including those in Europe, Asia, and emerging markets. Their situation is more complex. They do not have the same level of control over core technologies as the U.S., nor do they have the scale or political structure of China to pursue full self-sufficiency. As a result, they face a strategic dilemma. Aligning too closely with one side may limit access to the other, while attempting to remain neutral may reduce their bargaining power. This creates a three-actor system with inherent instability. The U.S. seeks to enforce technological boundaries. China seeks to break or bypass those boundaries. Other countries seek to navigate between them without being excluded. The tension between these objectives generates a dynamic environment, where policies, alliances, and supply chains are constantly being reconfigured. From a game theory perspective, this can be seen as a multi-level coordination problem. Each actor must make decisions under uncertainty, anticipating the actions of others while protecting its own interests. The result is not a stable equilibrium, but a continuous process of adjustment. Policies are introduced, countermeasures are developed, and new strategies emerge. For businesses and operators, this system introduces a layer of complexity that goes beyond traditional market analysis. Decisions about where to source hardware, where to host data, and which platforms to use are no longer purely economic. They are embedded within a geopolitical context that can change rapidly. Understanding the incentive structure of each actor is therefore essential for making informed strategic decisions. To understand compute sovereignty at a structural level, we need to move away from narrative and toward a layered framework. The most effective way to model this system is as a three-layer stack: hardware, infrastructure, and model. Each layer represents a different form of control, and more importantly, a different form of dependency. At the bottom is the hardware layer. This is where semiconductors are designed and manufactured. It includes advanced fabrication capabilities, access to extreme ultraviolet lithography, and the ability to produce high-performance chips at scale. Control at this layer is the most fundamental because it determines who can physically access compute. Without chips, there is no compute. Countries that lack this capability must import it, and that immediately introduces dependency. The second layer is infrastructure. This includes data centers, cloud platforms, networking systems, and, critically, energy supply. Compute is not just about chips, it is about running those chips at scale. Training large AI models requires enormous amounts of electricity, cooling systems, and stable grid infrastructure. This means that even if a country can import chips, it still needs domestic capacity to deploy them effectively. Infrastructure becomes the operational layer where theoretical capability turns into real output. The third layer is the model layer. This includes training data, algorithms, talent, and software ecosystems. It is the most visible layer, often associated with applications like generative AI, enterprise automation, and decision systems. However, it is also the most dependent layer. Without control over hardware and infrastructure, model development becomes constrained. Companies may build applications, but they do so on rented compute, under terms defined by external providers. The key insight is that this is not a flat system. It is hierarchical. Control flows upward. If you do not control the lower layers, your autonomy at the upper layers is limited. This is why countries without semiconductor capabilities often find themselves locked into platform dependency. They can innovate at the application level, but they cannot fundamentally alter the system. This framework also reveals Taiwan's structural position. Taiwan, through TSMC, holds a dominant position in the hardware layer. This is a significant strategic advantage. However, at the model layer, Taiwan is relatively absent. There are few globally competitive large-scale AI models originating from Taiwan. This creates a structural asymmetry, strong control at the base, limited presence at the top. This asymmetry is not necessarily a weakness, but it is a strategic tension. It raises a critical question. Should Taiwan move upward in the stack, or should it reinforce its position at the hardware layer and leverage it as geopolitical capital? There is no obvious answer. But ignoring the question is not an option. Ultimately, the compute economy framework provides a way to diagnose positioning. It forces both policymakers and businesses to ask, which layer do we control? Which layer do we depend on? And how does that shape our strategic options? Different countries are responding to the compute sovereignty challenge in different ways, but their underlying objective is consistent: reduce dependency and secure strategic autonomy. The variation lies in the tools they use and the layers they prioritize. The United States has adopted a dual strategy. On one hand, it uses export controls to restrict access to advanced technologies. On the other hand, it invests heavily in domestic production through policies such as the CHIPS Act. This combination of restriction and reinforcement allows the U.S. to maintain its technological lead while shaping the global distribution of compute. It is a classic example of offensive and defensive strategy operating simultaneously. China's approach is fundamentally different. Rather than relying on external systems, it is building a parallel ecosystem. Companies like Huawei are developing alternative chip architectures, while firms such as Baidu are investing in domestic AI models and platforms. The Chinese government plays a central role, coordinating investments and aligning incentives across industries. The goal is not immediate parity with the U.S., but long-term resilience. The European Union faces a different set of constraints. It does not have the same level of control over semiconductor manufacturing, nor does it operate under a centralized political system like China. As a result, its strategy focuses on regulation and coordination. Initiatives such as Gaia-X aim to create a sovereign cloud infrastructure, while the AI Act establishes a regulatory framework that reflects European values. The EU's approach is less about dominance and more about governance. India represents another model. It is leveraging its scale and growing digital economy to build domestic compute infrastructure. Government-led initiatives are focused on creating data center capacity and supporting local AI development. India may not control the most advanced chips, but it is positioning itself as a major hub for AI deployment and application. What is important across all these cases is not the specific policies, but the underlying logic. Each country is identifying its constraints and designing strategies that align with its strengths. The US leverages technological leadership. China leverages state coordination. The EU leverages regulatory power. India leverages scale. For other countries, including Taiwan, the implication is clear. There is no single template. Strategy must be context-specific. The key is to understand where you sit in the global system, and to design policies that maximize your leverage while minimizing your vulnerabilities. To move from theory to reality, we need to examine the quantitative structure of the compute economy. The first and most striking feature is concentration. A small number of companies control a disproportionately large share of global AI compute capacity. In the United States, major technology firms such as Google, Microsoft, and Amazon dominate the infrastructure layer. Together, they operate massive data centers and cloud platforms that serve as the backbone of global AI development. Estimates suggest that the top 5 companies control more than 60% of the compute used for training advanced AI models. This level of concentration is unusual even by historical standards. It means that access to cutting-edge AI capabilities is effectively mediated by a small group of actors. For startups, researchers, and even governments, this creates a dependency on external platforms. At the hardware level, the asymmetry is even more pronounced. Advanced AI chips are primarily designed by companies like NVIDIA and manufactured by a very limited number of foundries. China's domestic alternatives, while improving, are estimated to lag behind by approximately 1 to 2 generations in performance. This gap is not just technical, it has strategic implications. It affects the efficiency of model training, the cost structure of AI development, and the speed at which new capabilities can be deployed. Taiwan occupies a unique position in this landscape. Through TSMC, it produces around 90% of the world's most advanced logic chips. This creates a significant leverage point. However, it also introduces risk. High concentration in a geopolitically sensitive region means that any disruption, whether political or physical, could have global consequences. Another critical variable is energy. Data centers are becoming some of the largest consumers of electricity in the world. Training a single large-scale AI model can require as much energy as thousands of households consume in a year. This ties compute capacity directly to energy infrastructure. Countries with abundant and stable energy supplies have a natural advantage in scaling AI operations. These numbers highlight a key reality. The compute economy is not evenly distributed. It is characterized by concentration, asymmetry, and interdependence. Understanding these dynamics is essential for anyone attempting to navigate or compete within this space. The rise of compute sovereignty fundamentally changes how we evaluate national competitiveness. Traditionally, metrics such as GDP, military capability, and diplomatic influence have been used to assess a country's position in the global system. These metrics remain relevant, but they are no longer sufficient. A new dimension must be added: independent AI compute capability. This dimension captures a country's ability to develop, deploy, and control AI systems without relying on external actors. It includes access to hardware, control over infrastructure, and the ability to train and operate models within its own jurisdiction. Countries that score high on this dimension can shape the rules of the game. Those that score low must adapt to rules defined by others. This shift has several implications. First, it creates a new form of inequality. Countries that lack compute capacity may find themselves excluded from high-value segments of the AI economy. They can still participate, but primarily as consumers rather than producers. This limits their ability to capture value and influence outcomes. Second, it changes the nature of alliances. In the past, alliances were often based on military or economic considerations. Now, access to technology becomes a central factor. Countries may align with others, not only for security or trade, but also for access to compute infrastructure. Third, it introduces new forms of risk. Dependency on external compute providers creates vulnerability. If access is restricted, whether due to political decisions, regulatory changes, or technical failures, entire industries can be affected. This makes resilience a critical component of strategy. For businesses, these implications translate into operational decisions. Companies must evaluate where their data is stored, which cloud providers they use, and how their AI systems are built. These are no longer purely technical choices. They are strategic decisions with long-term consequences. In summary, compute sovereignty adds a new layer to the concept of competitiveness. It forces both countries and companies to rethink their positioning in a world where technology is no longer neutral, but deeply embedded in geopolitical dynamics. Given the complexity of the compute sovereignty landscape, decision-makers need a structured way to evaluate their position. A useful approach is to focus on three key questions that capture the core risks and dependencies. The first question is, where is your compute coming from? This requires a clear mapping of your infrastructure. Are you relying on a single cloud provider? Are your workloads concentrated in one region? Understanding the origin of your compute is the first step in assessing risk. The second question is, what happens if that compute is disrupted? This is a stress testing exercise. If access to your primary compute provider were restricted, how long could your operations continue? Do you have alternative providers, or would your systems fail immediately? This question forces organizations to confront their level of resilience. The third question is, do you have a diversification strategy? Just as companies diversify their supply chains, they must also diversify their compute sources. This may involve using multiple cloud providers, investing in on-premise infrastructure, or partnering with regional data centers. The goal is not complete independence, which may be unrealistic, but reduced vulnerability. These questions apply not only to businesses, but also to governments. Policymakers must decide whether to invest in domestic infrastructure, form strategic partnerships, or rely on global platforms. Each choice involves trade-offs between cost, control, and flexibility. The key is to move from implicit assumptions to explicit strategy. Many organizations operate under the assumption that compute will always be available. This assumption is no longer valid. By systematically evaluating their dependencies and risks, decision-makers can develop strategies that are robust under different scenarios. Ultimately, the decision framework is about awareness and preparation. It does not eliminate risk, but it allows organizations to manage it proactively rather than reactively. Compute sovereignty is often framed as a technological issue, but this framing is incomplete. At its core, it is an incentive system operating at the level of states. Each country is acting to maximize its own security, economic advantage, and strategic autonomy. The technologies involved, chips, data centers, AI models, are simply the tools through which these incentives are expressed. When viewed through this lens, the current dynamics become clearer. The United States is not restricting chip exports arbitrarily. It is aligning its actions with its incentive to maintain leadership. China is not investing in domestic alternatives out of preference, but out of necessity, driven by its incentive to reduce dependency. Other countries are not hesitating because they lack vision, but because they are navigating conflicting incentives. For operators, this perspective leads to a critical realization. The question is no longer which AI tool should I use. It becomes, whose system am I operating within? Every AI tool is built on top of a stack of infrastructure that is ultimately controlled by a specific set of actors. Those actors have their own incentives, which may or may not align with yours. This alignment matters. It affects not only access to technology, but also the values embedded in models, the rules governing data, and the stability of your operations. Ignoring it is equivalent to ignoring the foundation on which your business is built. The transition from a globalized technology market to a fragmented system of sovereign compute is already underway. It will not happen overnight, but the direction is clear. Companies and countries that recognize this shift early will be better positioned to adapt. Those that do not may find themselves constrained by forces they did not anticipate. In the end, compute sovereignty is not about predicting the future. It is about understanding the present with greater clarity. The structures are already in place. The incentives are already driving behavior. The only question is whether you are aware of them, and whether your strategy reflects that awareness.